Welcome to our experiment on lift with the 4 to Soar program. Here is our lift apparatus. We've used Knicks to make our apparatus. However, you could also use wood or other materials, and you can find more information about how to make our apparatus on the Hiller website looking under Education Curriculum. The basic components of this apparatus include a wing, which is vertical. We have a small modified protractor. We have a drag card right behind. And we have a very important arm that sticks out to help for measurements. Notice when I move this, it's very smooth. It needs to be free-flowing, otherwise you'll have trouble with all of your results. So here we're going to talk a little bit about how our lift apparatus interacts with our fan. The fan is our source of wind for this experiment. To use our fan, you want to line it up so that it's facing directly on the wing. I like to have it about 6 inches. Adjust, see what gives you a very consistent and steady result. On the fan, the person who's going to be in charge of the fan, they're going to need to adjust the dial to 3 when we want to turn on the fan. As they do that, they will need to hold on to the fan because these ones have a tendency to slip northwards. Well, if they go up, it's no longer directed at our wing, so it won't help with our experiment. Let's see if I can adjust this back now. Okay, let's talk a little bit about this lift apparatus. Let's look at the wing. Our wing is vertical, so this helps us with just measuring angle of attack and to determine what is the best angle of attack in terms of lift. When we adjust our angle of attack, we have a protractor beneath the wing. I like to line up the protractor so that the protractor is behind this drag card or these 2 bars beneath the wing. When that's stable, I turn my wing on the positive numbers, so it could start at 0, 10, 20, 30, 40, 50 degrees. That's the angle of attack. What students will notice as they go through this is that the results will change as they measure on the scale. The third person in this experiment, or fourth, could be down here measuring the results against each angle of attack. So here is our lift apparatus. We're going to be adjusting for angle of attack. Notice the protractor right behind the wing. We line so that these 2 lines on the protractor are the same as the bars or the drag card below the wing. So here our wing can adjust over into the positive numbers. I prefer the positive numbers because then we'll have positive results on our scale. The negative numbers still may produce lift based off of angle of attack, but we don't need to measure that today. So we're going to adjust this right now to 30 degrees angle of attack. I look, make sure that the arm of our apparatus is set at 0, and I start the fan. I'm putting the fan on 3, which is the strongest setting. You'll notice that after we generate lift, the arm should steady out at a certain point. Then we can turn off the fan and measure how strong of a lift we generated. Here we're at about 15 degrees, or 15 on our scale. So your students will work in groups of 3 or 4 to complete this experiment. They'll go through 1 trial all the way, testing 0 degrees through 60. If time permits, then I suggest they go on to a 2nd or 3rd trial. What they'll notice is the best results will happen at about 20 degrees. This is important because for a real airplane, the best results are close to 17 degrees. The second thing they may notice is that the results significantly drop off as they continue on with the angle of attack. This effect is a stall, and in a real airplane, if they go past that 17 degrees, they will be stalling the wing and their airplane will no longer be generating lift.
This is our drag car. It's used for It's a Drag, one of the aerodynamic lab activities included in the Soar curriculum. For this case, we're going to be investigating drag with a small propeller car. For traveling flight science lab purposes, the propeller cars come pre-made for you. If you're implementing this in your classroom at an institution that's not participating in the traveling flight science lab, you can build it out of everyday materials. We've used a balsa airplane to provide the motor stick and the propeller. The rubber motor is attached right about here. We have a piece of card. This is 3 inches by 5 inches. That's taped along the motor stick right here. At the top there's a straw which will allow us to place it on the fishing line. And here's our landing gear. It's a strip of cardstock. The landing gear looks like it's facing the wrong way, but for our purposes this is going to increase the amount of drag. And with a little piece of tape here, we can move it from fully extended, partly extended, and fully retracted. This will allow us to vary the amount of drag. When the time comes, we're going to put a calibrated number of turns on the propeller. Once the propeller is turned, we'll release it, and that will propel it along the fishing line. We'll then be able to measure how far it goes with the landing gear in different configurations. Let's see how that works. Here we see the drag car set up on its line. The fishing line, about 10 meters worth, is stretched between two ends that are about the same height above the ground. Doesn't have to be perfect. We want to make sure that the car won't slide due to gravity. And it also needs to be pretty tight so that it won't sag too much. So now it can move freely with the fishing line with a minimum of friction. We're going to test this in several different positions so that we can fill out our data sheet. We're just going to do one trial for purposes of our tutorial. We're going to begin with the landing gear fully extended. We're going to go to the starting spot. Now our starting spot's not all the way against the wall because we won't be able to maintain that as a constant as we change the position of the landing gear. In my case, I'm in the Hiller Aviation Museum's theater. I'm going to start right from the edge of these airline seats. And if it's plus or minus a few centimeters, that's going to be okay. But this is going to be our measurement point. Now for our purposes, we've determined that we're going to use 60 turns for each and every trial. That way we're going to impart the same amount of energy to the car to launch it down the drag track. "60 turns. We're going to give it a launch and see how it goes. Don't follow it. Now we've adjusted our landing gear to half extended, 45 degrees, and we'll launch it from exactly the same starting point. For our final test, we're going to move the landing gear to the fully retracted position so that the edge is now parallel to the direction of motion. Same starting point, start the propeller, and off it goes. Once the drag car has come to a complete stop, we can measure the total distance traveled using the tape measure. I'll have my partner at the far end hold it at the starting point, not where it's necessarily attached to the wall, but at the starting point. And then we can measure from a constant point on the drag car. In this case, we're going to use the end of the straw. The end of the straw is 6 feet 11 inches from the starting point. Using repeated trials, we can compare how far that distance is for fully extended landing gear, partially retracted, and fully retracted landing gear, and that will allow us to analyze the effect of drag on our propeller car.
Welcome. We're going to take on our thrust experiment. Now, when the students are doing this, they'll be working in groups of 3 or 4, which will come in handy, especially because you may find you may have too few hands. So first of all, I do like to remember that safety is important. Even though I wear glasses, I don't like to get too many scratches in them. So I put my goggles on. Now, in the back of our experiment, we mentioned our pen scale. It's attached with a little string back here. Make sure that the pen scale is facing the top so that it's very easy to read your results. what you're going to be measuring are these different angles for our propeller blades. How we do that is a protractor. Basic protractor, we're going to be working from this point in the center out to the various numbers to get our angles. All right, so we're going to be adjusting our propeller blades using our protractor. I like to line this part of the protractor up with the length of the car. Here, our propeller blade, we're looking for 90 degrees, so it's helpful to have a ruler. I take my ruler, giving me a nice straight line. Oh, it doesn't look like my propeller blades are lined up. This is when it's useful to have a partner. Someone can come in, hold that at 90 degrees, you can adjust it. You turn the propeller blade, trying to keep a hold of that car, and you adjust it again. A third person, this is one of the favorite jobs, can get in here with the alligator clip. They squeeze here and you can see the alligator's mouth opening. You come down holding the wheels so that the propeller car does not move. You clip on. It'll make quite a bit of noise and should start to go forward. Sometimes we give it a little tap. We read our results and then we turn it off. Students will complete trial 1 going through the different degrees, 90, 80, 70, 60, 50, and 40. If time permits, then they can go through a trial 1, 2, 3, and more. What they'll notice is the results between 80 and 70 degrees tend to be the best performance.
That concludes our overview of the NASA Traveling Flight Simulator Lab flight simulation activities and the Soar Aerodynamics Lab. For additional resources, go to our website at www.hiller.org. Go to our education page and from there navigate to teacher resources. Good luck as you take to the skies with your students.